right now, tonight. Look up. You are staring at a collision already happening. Not fireballs, not shattered stars, something quieter than that, far stranger too. You already know the headline. Andromeda hits the Milky Way in 4 billion years. People repeat that number like trivia, a fact so distant it barely registers as real. But here's what nobody asks. If the impact is 4 billion years off, why do astronomers say they already touch? What would you detect standing at the actual first point of contact? Is there even one definable minute one for something built from a trillion stars? Andromeda hits us in about 4 billion years if you're measuring by starlight, but the invisible outer skin of both galaxies may have already met. The real minute one of this collision might not be in our future at all. It might already be behind us. Start with what you can actually see. Andromeda sits roughly 2.5 million light-years away. Its glowing disk of stars spans about 152,000 light-years across. That's the galaxy everyone pictures, a bright spiral patiently waiting to arrive. But that familiar picture is incomplete. Wrapped around that disk is something almost nobody imagines. A halo, not of light, of gas, thin ionized plasma. It produces no glow of its own. Point a telescope straight at Andromeda, and you won't see it directly. You can only see its shadow cast onto someone else's light. Astronomers found that shadow using 43 background quasars. Those quasars blaze in ultraviolet, sitting far beyond Andromeda itself. Their light crosses Andromeda's hidden halo on the way to us, and the halo leaves fingerprints on that light as it passes through. Quasars work perfectly for this because of where they sit. They burn from the centers of galaxies billions of light-years further away. Their light has to cross almost the entire depth of Andromeda's halo. That long path is exactly what makes faint gas detectable in the first place. Here's the discovery behind that method. Nicholas Lehner at the University of Notre Dame led a project called Omega. His team pointed Hubble's cosmic origins spectrograph at those 43 quasars. Each quasar sat at a different angle relative to Andromeda's center. That gave the team dozens of separate slices through the halo. It worked almost like a CT scan of something invisible. They measured exactly how much ultraviolet light Andromeda's halo swallowed at every angle. The full results appeared in the Astrophysical Journal in 2020. They were startling. Andromeda's plasma halo reaches roughly 1.3 million light-years from its center. Before this study, most models of Andromeda's halo relied on theory and extrapolation. Lehner's team turned that guesswork into an actual, directly measured boundary. The cosmic origins spectrograph made this possible for a specific reason. It was built to split ultraviolet light into incredibly fine wavelength slices. Only that kind of precision could catch gas this thin and this cold. Sit with that number for a second. 1.3 million light-years is not a thin skirt hugging the disk. It's halfway to us. And it isn't even uniform in every direction. In some directions, the halo stretches nearly 2 million light-years out. It's built from 2 distinct layers, stacked one inside the other. An inner shell is turbulent, churned by supernova outflows. That inner layer reaches about 500,000 light-years. Beyond it sits a hotter shell, smoother and calmer than the turbulence closer in. That outer layer runs somewhere between 1 and 2 million degrees Kelvin. For comparison, the surface of our own sun burns at about 5,800 Kelvin. This outer shell runs hundreds of times hotter than sunlight, yet it emits no visible glow at all. The gas is simply too thin to radiate like a star. The Milky Way almost certainly carries a matching halo of its own. We just can't map it from here. We're standing inside it. Now do the math nobody says out loud. The total gap between us and Andromeda today is about 2.5 million light-years. Andromeda's halo alone reaches out 1.3 million light-years. Now add the Milky Way's own halo reaching back the other direction. Those two envelopes are no longer separated by empty space. Somewhere in the dark between us, they already overlap. Picture 2 people standing in a large, dark room. Each one carries a faint cloud of warm breath, invisible in the dim light. Long before their hands touch, the moist edges of that breath start mixing. That mixing is happening between us and Andromeda right now. We'll come back to exactly how you'd detect it. That single fact rewrites the entire headline. Nearly every explainer treats the collision as something starting later, something that begins only once the visible spiral disks finally meet. That meeting is supposedly 4 billion years away, but the measured reality tells a different story. The outermost material of both galaxies already shares the same territory in space. By one entirely legitimate scientific definition, first contact isn't scheduled for the future. It has arguably already begun. Think about how strange that actually is. We tend to imagine cosmic collisions as single dramatic moments, a before and an after, separated by a flash. This one doesn't work that way at all. It has stages, and we are already standing inside the first one. So how would you actually detect a collision hiding in plain sight? You don't look at the gas directly. You look at what the gas removes from someone else's light. A quasar sits billions of light years beyond Andromeda. It blazes brightly in ultraviolet wavelengths. Its light travels for millions of years before reaching us. Along the way, it passes straight through this thin plasma. Specific wavelengths get absorbed during that long crossing. It works the way a filter stains white light. Astronomers read those missing wavelengths like a fingerprint left in the dark. That fingerprint reveals the gas's presence. It reveals its density too. It even reveals its temperature and its motion. Minute 1 of contact isn't a flash you could photograph. It's an absence, buried inside someone else's ancient light. And that absence sat there for millions of years, waiting. It waited for an instrument that didn't exist until recently. If halo contact already counts as hitting, everything else shifts. The version everyone pictures, two bright disks colliding, is a far later chapter. That visible meeting starts only once the galaxies close most of the remaining gap. About 90% of it. And closing that gap isn't fast. It isn't violent either. The process runs on something astronomers call dynamical friction. Picture two enormous clouds of dark matter, each one dragging on the other's motion, like a spoon slowly stirring honey. Every orbit around each other bleeds off a little more energy. That energy loss forces the galaxies gradually closer together. Think of it less like a collision course and more like a very slow dance. Each pass brings the two galaxies fractionally closer. Every loop shaves a little more speed off their mutual orbit. Dark matter doesn't collide the way gas does. It simply exerts gravity on everything nearby, including itself. As the two halos pass through each other, their combined gravity quietly reshapes both orbits. Momentum trades hands instead of any actual impact happening. The whole process plays out across hundreds of millions of years. Now the story shifts from mechanism to memory, from how this happens to what astronomers actually believed about when. For over a decade, one story dominated the science completely. A 2012 Hubble study measured Andromeda's sideways motion. Roland van der Merel and Sangmo Tony Son led that research. Andromeda's sideways drift looked nearly negligible in their data. A direct, head-on hit seemed almost guaranteed as a result. Astronomers built entire animations around that near certainty. That certainty cracked in June 2025. Till Soala and colleagues at the University of Helsinki published new work in Nature Astronomy. They folded fresh Gaia satellite data into their models. They also added gravitational tugs the earlier study had underweighted. Those tugs came from the Triangulum galaxy and the Large Magellanic Cloud, two smaller galaxies subtly bending the bigger picture. The team ran 100,000 separate simulations to test the outcome. Their results were striking. Only about a 50% chance existed for any merger within 10 billion years. The odds of the dramatic 4 to 5 billion year head-on scenario fell hard. Just 2% of their simulations produced that classic outcome. The difference came down almost entirely to sideways motion. Earlier estimates of Andromeda's transverse velocity carried larger uncertainties than anyone fully appreciated. Even a small correction to that drift changes the outcome dramatically. A near miss and a direct hit start from almost identical numbers. Here's the uncomfortable lesson inside good astronomy. Confidence in any forecast depends entirely on measuring sideways drift with precision. And that precision keeps improving with every new satellite. So the 4 billion years half of this title is now a probability. It is not a certainty anymore, not by a long shot. But suppose the merger does eventually happen anyway. Suppose the visible disks genuinely do meet someday. What would that actual moment look like up close? Not an impact, nothing crashes. Stars sit unimaginably far apart from one another. On average, roughly 1075 astronomical units separate neighboring stars. That's over 100 times the distance between Earth and the Sun. When two fields that empty slide through each other, nothing collides. Positions shift slightly, and gravity nudges a few orbits, but the two star fields essentially pass straight through one another. Picture two thin veils of light drifting past each other in the dark. Even a direct hit between galaxies is mostly empty space passing through more empty space. The real action happens in the gas, not in the stars. You don't have to imagine that outcome from scratch. You can watch it happening somewhere else right now, 60 million light-years from here. The antennae galaxies carry the catalog names NGC 4038 and NGC 4039. They sit about 60 million light-years away from Earth. Astronomers watching them don't see stars smashing into stars. Instead, they see something else happening. Enormous clouds of gas compress and shock heat against each other. That compression triggers brilliant new bursts of star formation. New stars ignite live inside that wreckage. Infrared images taken years apart capture the change. It's the exact silent overlap mechanics Andromeda and the Milky Way are heading toward, just further along the timeline. Astronomers estimate their encounter began several 100 million years ago. It will likely continue for hundreds of millions more. Two long streamers of stars and gas trail off the antennae galaxies into space. The same gravitational tides now working between us and Andromeda flung them out there. Neither streamer contains a single star that struck another star. Every bright knot inside them is newly born gas, not wreckage from any impact. There's one more layer buried underneath all of this. A less formal analysis of published halo mass data points to something extra. The Milky Way's dark matter halo is separate from its plasma halo entirely. That dark matter halo may stretch roughly 350 kiloparsecs outward. That's over 1.1 million light-years, reaching well past the halfway point. Define contact by gravity instead of gas, and the picture shifts again. The two galaxies' spheres of gravitational influence likely overlapped long ago. That's a second candidate for Minute 1. Quieter and older than the plasma halo zone. Nobody has directly imaged that dark matter overlap like Lehner's team imaged the plasma halo. Dark matter doesn't absorb quasar light the way ionized gas does. Its presence gets inferred instead, through its pull on galaxy rotation. That's weaker evidence than an absorption line, but it points the same direction. Two invisible spheres, quietly touching long before anything visible does. Remember that dark room from a few minutes ago? Two people standing apart, each wrapped in a cloud of warm breath you can't see. You'd only catch that mixing air by shining a specific color of light through it. Watch closely, and you'd see exactly how much light gets absorbed. That mixing breath is the two galaxies' halos, overlapping right now, above your head tonight. The eventual handshake, the visible disks actually meeting, is the 4-billion-year event everyone talks about. But by the breath cloud measure, something has quietly already started. So where does that leave the number in the title? Let's widen the view and pull it all together. The halo Lehner's team measured already reaches halfway across the gap. That overlap means material from both galaxies is touching today, not someday. We can only detect that touch through ancient quasar light. That light silently records the contact, one missing wavelength at a time. The dramatic, visible merger everyone imagines is real, but it's a much later stage of the same story. It only arrives once the gap closes through slow gravitational drag, never through a sudden crash. Even that later merger's old certainty just took a hit. What looked settled in 2012 fell to a 2% chance for the classic version. When it eventually arrives, the visible collision still won't look like an impact. It'll look like two vast fields of starlight sliding calmly through each other, the same thing already visible tonight in the antennae galaxies. Underneath this story, an older overlap of dark matter kept running the whole time. The number in this video's title was built to sound like a countdown towards some unimaginable future. But the real first contact doesn't wait for any countdown to finish. It's defined by the outermost material either galaxy possesses, and that material is arguably touching right now. It's written into the absorption lines of ancient quasar light. That light left its source before Earth existed. Somewhere out there, that beam still crosses the exact seam between two galaxies' halos, the true minute one of this collision, already past, already unseen, already here,